Hi, welcome to the MPI workshop presented by the NSS XSEDE program. This was originally a 2-day event with hands-on exercises that you can view at your own pace.
Now we'll take the opportunity, though, to look at all the other parts of MPI that we haven't had the opportunity to get into. And I think you should be exposed, at least, to all of these things. Also, this will help to kind of dispel any anxiety you may have that, oh, we're only using, 15 routines or so far, and I know that as I look through the documentation, I see these hundreds of other routines. Is it the case that I don't understand most of what MPI is? It's not the case. As we'll see, these are really a lot of convenience functions that group together in families, and it's not difficult to understand the vast majority of them based upon what you already know. Just by saying, oh, I can see this is a variation of something that I might find useful under different circumstances. So that's how we'll actually approach the topic here. I've kind of grouped them together into these areas of functionality, not just encyclopedically going through the index here. And as we explore these, I think you'll also find it's kind of neat in that the committee over the years has really been driven by functionality by scientists that are trying to get things done, and they've added in a lot of very powerful functionality that allows you to attack problems, practical problems, in ways that just make your life a lot easier, make the code maintainability a lot better, and at the same time bring good performance into the mix. So let's explore some of those. This is the list of things that we will go through here. So there are a number of different areas, but again, they group together pretty intuitively as we jump into them. The standard has evolved. I'll briefly mention how the standard has evolved because it does give you some context here. The standard has evolved since its first deployment back in the early 90s, when it was actually an evolution of something earlier called PBM. Message passing, a standard, at least necessity for standard, grew with the first massively parallel machines in the late 80s, and this PBM kind of standard had emerged. And that committee, a lot of the people in that group and that committee reconvened and said, okay, let's do this, and let's do this correctly and start with a new standard based on our prior understanding. And so even the 1.0 version of the standard had an awful lot of everything I think we've used so far, an awful lot of what we'll look at today. It was more mature than you might think of at the time, and consequently it was rapidly adopted and widely used, and became pretty much the standard for doing message passing type of scalable computing in the 90s. And already by 96, they had recognized that there was an opportunity to add some more functionality into it. And so MPI-2 added in a few of the areas we'll look at here, in particular MPI-IO, way of doing I/O, which, as I mentioned earlier, becomes inevitably important for a lot of projects as you scale up, and a few other things. It's not some obvious layer on top of things. As we look through all the different topics, things are intermixed kind of gradually as they've added on to it. It's not like all of a sudden the versions of the standard have some vastly new direction that they've taken things off in. And the standard continued to evolve, became, again, the norm by the turn of the century. There was virtually nothing that was done on large scalable systems that wasn't MPI. And then recently, as exascale systems started to show up on the horizon and large codes running at hundreds of thousands of cores were becoming less exotic, the need to address some performance issues with those 100,000 plus million core jobs became important, and the MPI-free standard came along and added in some of the missing pieces there, or at least standardized some of the techniques and approaches that were being used. So it's been a nice gradual evolution over a long period of time, driven by a committee that's been very concerned with keeping scientists being productive as opposed to demonstrating some unique computer science approach or novel new paradigm. So let's jump into the first topic here. It's one that you'll find, probably almost all of you will find useful and convenient and friendly and easy to use, which is user-defined data types. So far, we've been passing around the built-in MPI types like integer or float, or maybe an array that's made up of those. We'll find very quickly, even in our Laplace code, opportunities to make life a little bit simpler if we can define a type of message that we're going to send around repeatedly. Or you might have a type of message that's maybe a little bit or a lot more tedious to construct, if you were sending around a diagonal of an array or sub-blocks of an array, for example. If you were dealing with the finite element code that had a very regular structure involved and you were sending out an irregular pattern of elements out of an array, these would all be things that you could deal with by sending individual elements in some fashion, but user-defined data types will make it very easy for us to do that. There's a purpose that's become somewhat obsolete that used to be kind of nifty, which was that in sending messages between hardware of varying types, for example, some hardware has what's called big endian, and other hardware has what's called little endian formats for floating point numbers, which is basically the order of bits in a floating point number. It's a low-level kind of format, hardware formatting thing that most of you will probably never be concerned with, especially as in the world today we've pretty much all settled on Intel kind of IEEE format floating point numbers. Things like that, it used to take care of behind the scenes automatically if you were building heterogeneous clusters, assembling a bunch of different machines into one cluster. That's become much, again, less important. But the second one here, which is putting together messages of your own nature, specific to your own application, is very convenient, and it helps performance a lot. The way you do this in MPI is a two-step process, very straightforward, to just create your own message type using some of the built-in MPI type definition routines that allow you to construct pretty much anything you can imagine as a data type. And once you've committed it, or excuse me, once you've created this and defined it properly, then you commit the type. The routines to create it, and I've got a handful of them here, and there are some more in the library, and you can very quickly pull them up in the index, cover all of the cases that you would think of in terms of what kind of message do I want to put together, how do I want to assemble a bunch of data. And I'll show you a bunch of examples here so you can see how flexible it is. So here are some of the basic ones. Let's step through a few examples. Here's the first one that might be useful in our Laplace code. We looked at our Laplace code decomposition yesterday, and I said one of the first things that might come to mind in breaking up a metal plate is to break it up into 4 squares. And I said that's a perfectly reasonable approach. We'll do strips instead. It'll make life a little bit easier. But if we were to break things up into squares, one of the first things you'd note is that while we're sending data that's contiguous in memory, like we're currently doing in our Laplace code, life is easy. We point at the first element and then say how many we want to send from that array. But if we wanted to send a column of that array, in the case of the C code here, then these elements aren't contiguous anymore. They skip through memory. How could we do that? Well, of course, we could brute force it by sending a bunch of individual elements or copying them into some separate array or something. But with user-defined data types, the solution is at hand. What we can do is, say, define our own type of column here. And when we define column, we use the MPI, one of the MPI type definition commands. The vector one allows us to define something that is just a long vector of information, as the name implies. And when we define vector here, the parameters that you'll see for it are how many of those we want. Well, we would want row number of vector of elements in our column vector, because that's how many rows we have defines how tall the column is. And then we can give it the stride, or the jump between elements here. And the jump between elements here is the number of columns we have. That's how many elements it goes from one to the next. And then basically we've defined a new data type called, we're going to call it column here, that we can now use anywhere in MPI that there's a data type parameter, in particular in our send. So here's our MPI send down below. And instead of sending a bunch of elements, we're sending one element, one column type here. And we point it at the beginning of the column, and we send one column type. So we can see this solves a couple of problems for us. It eliminates the need for us to kind of create a column of our own every time we want to send a message. It's much nicer and easier to read and maintain in the code. And it also, performance-wise, this is one of the reasons why user-defined data types are so convenient, is that they not only clean up our code, but it's much better performance because the MPI system behind the scenes takes advantage of any hardware that's out there that can gather all of these elements together efficiently. And it so happens that most modern processors or even network interfaces have the ability to go out and gather columns of data scattered regularly through memory much faster than you would one by one. And so when we've defined this data type, we've also given the system behind the scenes the opportunity to do it much more efficiently, gather this data efficiently. And this would be a very efficient operation to do in MPI. So we cleaned up our code, made life easy, and we've now got an implementation of our Laplace code that would work with these square elements in the array very nicely. As a matter of fact, so nicely that we've even taken the opportunity here to define a row, even though we've already got a nice functioning row routine, right? We can just point at the beginning and send, 1,000 of these. Why not take the opportunity to find a row data type too? And now we can also send one row instead of having to gather a bunch of them together. So it's very straightforward to apply this Laplace code. If you'd like to experiment with it, that wouldn't be a bad place to start. But let's look at some more complex examples here, where it might not be so obvious how to do things. Here's a schematic of a molecular dynamics code, which means essentially we've got a code where a bunch of molecules are bouncing around in space off of each other and perhaps off the walls. And we're modeling this as it evolves in time. And most approaches to this will break up the space, do the data decomposition in this case, by breaking up the space. And if you break up the space with a molecular dynamics code, you'll find that molecules over time enter and leave the boxes or the processors, the PEs that are responsible for that space, as the model evolves in time. In this case here, I'm suggesting that these three molecules, for example, might be migrating to the left here on their way out. And so what you would typically do is you'd send those as a message to the PE over here and say, hey, you've got three molecules incoming that you're going to be responsible for as long as they're within the space of your box. Well, if we had in memory a particle list here of all the particles that are in our PE right here, and we want to send out three of them, in particular molecule 1, molecule 5, and molecule 6, as a message, we can define, using the index type in MPI, we can define a message that points to an index. We give it a bunch of indices that point then into our data structure that has those, and it will create a message that consists of the elements of those particular indices. So it gives us a way to combine, make a simple message. This also illustrates something that might be a surprise to people that are seeing it for the first time, which is that we're creating a message type here that's only used for one iteration of our code at one point in our code. The Laplace code would define our row and our column. We use them throughout the code. Here we're defining a message type that's only going to be valid for sending these three molecules over, and then it's really not good anymore. We've got, as a matter of fact, we have to free the message type up here so that we can create more of them every time step. And you might say, is that worthwhile? If it's changing every time step, wouldn't it be just as efficient for me to go and gather this data together myself and create some kind of a message? And the answer is that, again, maybe surprising you to know. The hardware that can go and gather this stuff for you behind the scenes is typically, again, very efficient. So this is not only perhaps a way to make your code a little clearer and more elegant, but it's also potentially an efficiency gain, in that creating messages, even if they're only used for one time step, can still allow the MPI system behind the scenes to do as best it can, probably better than you, at gathering this data up, putting it into a message, and sending it on its way. So it's not uncommon to see user-defined data types that are repeatedly defined and then freed. And again, if you do define something with the intention of using it for one time step, you do want to make sure at the end of that time step that you free it up, which is what we're doing here. So here's a very simple example of we create from our existing data structure, we create an index list that points to the particles that we want to send. We commit that type. We use it to send a message of 1. So we've got one of this buffer type message that we've just defined and created, and then we free it up. And we do this every time step as the molecules bounce around. On the receive side for this, we can receive things as a bunch of particles here. So here we're receiving them then as individual particles if we want, or we could receive it as one message, however we'd like to do it. An important thing to point out here is that dynamic memory allocation is very, very common. I'm sure many of you right now, not most of you probably, recognize that in problems, particularly problems like this, where you've got things that are changing from time step to time step, you're very often dynamically defining your data structures. These arrays are not predefined and static at the beginning of the code. Instead, as things evolve, or even if they're defined at the beginning of the code, they may be dynamically defined there. They're not static structures, but they may change throughout the run of your code. MPI interfaces very, very well with dynamically allocated data structures. Again, it's driven by scientists to recognize codes are full of dynamically allocated things. And so if they are dynamically allocated, that's fine too. You can check and see before you receive the message how big it is so that you can allocate enough space for it. How can you check the size of a message you haven't received yet? MPI probe is an easy way to do that. We can probe for a message that's coming in to see how big it is, because we don't know how many molecules are coming our way. It so happens there's 3 molecules this time. Might be 300 next time, and there might be 1. And so we can probe the message and see how big it is before we actually receive it. We can get the count of how many we've got, and then we can define in memory, in this case with the malloc here in C. So any of you that are C programmers are comfortable with mallocing memory. Fortran programmers, you can set up an allocatable array. So now that we know what's coming in, we can define or allocate enough memory for it, and now we can receive into a buffer that's been properly sized here to incoming particles. And so dealing with dynamic data structures is no problem at all. And by the way, MPI, again, because it's very practical, deals with padding as well. We'll get into padding a little bit more, I think, maybe the next slide or so when we talk about structures. But basically, it's the math for how much memory something takes up is not always as simple and straightforward as we might hope. We'll come back to that issue in a bit. Anytime you're dealing with dynamic memory or memory in MPI, you might have to deal with memory addresses, pointers to those, and in which case the type that shows up in MPI is MPI aint, address type integer, and that will allow you to give pointers to any of the MPI routines or receive pointers from any of the MPI routines that want to deal with memory pointers. In this case here, we've got a type that sends data from a linked list. Before we were sending our molecules from the statically defined list. Very often, you'll have in your code instead some list of elements that you've created in memory and that's scattered all over memory in some pattern. It's not one array, and the indices are no longer now pointers to an array and the locations in the array. Now the indices are pointers to something that's scattered all over memory. Again, a linked list would be a good example of that. If we've created some data, molecules, for example, are really a linked list, and they're allocated all over the place in memory. Now for our data type, we wish to point it to some particular molecules in that linked list. And we can do that just fine using the h-index type. And so we can see we create an h-index type type here, and when we create it, we give it a list, we tell it how many there are, and then we give it a bunch of pointers to each one of those elements, memory pointers to those elements. That's what happens here in this loop. It's going through and giving the pointers to each one of these things, and now we've got a new message type, and we can just send one of this message type here, and it will go through memory and collect all of those things as best as possible, and send that as a message. Once again, this is the type of message that you're defining iteratively through the run of the code, so we'll free it up here until the next time step when we do the same thing again. So dealing with dynamic memory, if you find yourself asking, can MPI deal with this? It can. It's built around the notion that many algorithms use dynamic memory. We could also pack a message of any particular type that we want by hand, so we can go ahead and keep incrementally packing items onto a buffer, and it will work very nicely. It has a position pointer that will auto-increment for us and tell us where to pack the next thing in, and then we can send this packed list. When we receive it on the other side, we can unpack it one at a time or receive it as a big chunk of things, wholesale, whichever one happens to fit your thinking better. We can also pack straight up struct types from C or Fortran types that you might construct yourself, which allow us to take something that in memory can be a bunch of different values, any arbitrary thing that you can create as a structure in memory, and we can send that as a single message. We can pack things together. This is where we start to pay attention, though, a little bit to this padding issue. So here's a struct right here, and we've packed it one element at a time, and that's great, and we send it out. So we've gone to the trouble to kind of deconstruct or select pieces from this particular structure to send as a message that we want to send out. And that works great, as you'd expect. However, you might want to send the whole struct straight up as a single message. That would be a very reasonable thing to do. You can imagine it, for example, for a molecule in our molecular dynamics code, the molecule might actually consist of things like, its mass and its position, velocity, or whatever, all in a nice bundled struct, and we want to send that as a message. So again, we could pull things out individually and create our message types, but we might very well just want to send a struct. The issue that shows up here with sending a C-type struct is that, in reality, a structure in memory is very often, depending on how you've built it and how much you're aware of this, is you pad it. It's got some extra bytes in there to keep things lined up in memory. Modern processors like things to be lined up on byte boundaries. They don't like things arbitrarily to be located. We might think addresses are bytes in memory, but in reality, processors much prefer and work much better if things line up on certain byte boundaries because they work better with the cache and whatnot. Those might be 8-byte boundaries or 4-byte boundaries. And so behind the scenes, the compilers usually worry about that for you. But you generally, if you do use a lot of structs, want to be aware of it, because if you have a lot of these, if you've got many arrays of this struct, you'll at least want to know where your memory is going. Why does each one of my structs, even though if I add it up here, for example, I might add this up and say this is 1 byte, and this is 4 bytes, and this is 8 bytes. So that should theoretically be 13 bytes. But if I look at a bunch of these in memory, if I have 100 of these in memory, I might think that's 1,300 bytes, and I look at it and go, but in actuality, this is 2,400 bytes. Where's my memory going? Well, where it's going is that The compiler and the processor abhor a character, an individual byte sitting there on some weird boundary, or things sitting on 13-byte boundaries, and it will line these things up. So it'll take the character, maybe if it's 1 byte, and pad it out with 3 more bytes perhaps. This is a very implementation-dependent thing. So this is again where MPI is very pragmatic. It recognizes that this is implementation and platform-dependent. Might change from one version of the compiler to the next what its padding strategy is. There are usually in most languages, most compilers, I should say, there are pragmas that allow you to kind of tweak this stuff and push it around. And so anytime you're dealing with structs, padding shows up. And so, again, MPI is perfectly capable of dealing with that. It has some routines that when you're dealing with structs allow you to get the addresses and figure out what the padding actually is and compensate for it so that the messages know how they should be padded, how they should grab the things, and how they should unpack them on the other side to deal with this padding. So it's straightforward. It's a little bit of bookkeeping, but it's important. It lets you deal with the fact that so often in your code, the perfectly natural data structure to send us the message is a struct, a C-type struct. I just mentioned here already the performance implications of this before we leave the topic here are not just for your syntactical convenience in your organization and your code. You might, matter of fact, think you're paying a penalty to use these user-defined data types instead of manually packing the data yourself. It's the opposite, really. If you use these defined data types, you're giving the system the opportunity to do things more efficiently behind the scenes, where hardware processors often do have the ability to go and collect things from memory in the most possibly efficient fashion. Okay, the next topic that you'll also inevitably find yourself taking advantage of as you go to, well, as you write pretty much any code, are some of the collectives. We've already used some of the collective routines in MPI with broadcast and reduce. A collective routine is any operation that all of the PEs in that communicator have to work on at the same time, like a barrier, like a broadcast, like a reduce. All the PEs have to participate in that collective routine. And we've seen how useful something like broadcast is. Let's look at some of the other really popular and useful variants that you're likely to come across or want to use yourself. Scatter does, as the name kind of implies, scatters a lot of data around from one of the PEs to other PEs. So you may have sitting on one of the PEs, the root PE, it can be any PE. Again, it often works out that it's PE0 is your root, but it could be any PE. One of the PEs might have some data, and other PEs should get selective pieces of that data. So in a simple case here, in the most straightforward case, we've got PE0 has this array here, and all the other PEs would like to get one integer out of this array. Each one of them gets a different integer, though. So it's not a broadcast. They don't all need all of this data. They each need selectively a piece of this data. And scatter allows us to do exactly that. We point at a buffer full of data, and we say, and it can be any data type again. In this case here, we've got a bunch of integers, and we say, scatter this data throughout the communicator, associated communicator, and each one of the PEs will get some subset of that data. Gather is the exact inverse of this, where all of the PEs have some data, and we would like to gather it together at some central point. It can be any one of the PEs. Again, it often turns out to be PE0 is the root. So all the PEs have some integer, and we would like to pull those together in some array here on PE0, and gather will allow us to do that. There are a lot of variations on this because it is so common, and there are so many versions that you might like to use in different algorithms. There are all versions of these, which mean that at the end of the process, all of the PEs get the result, not just the root. You can think of the all routines as equivalent, functionally at least, to you doing a gather and then a broadcast. So all reduce, I mentioned briefly yesterday, for example, a reduce operation is, say, finding the sum of a bunch of numbers scattered through PEs. If we said we reduce, gets that sum and gives it the PE0. Well, all reduce gets that sum, and then instead of PE0 having to broadcast it out, they all end up with that sum. The all versions of the gather and scatter are the same kind of thing. The all gather means that, or I should say for gather, it doesn't make sense for scatter. The all versions of gather gather all the data together and then make sure that each one of the participating PEs gets a copy of it. All to all allows each one of the PEs to send data to in some regular pattern to all of the other PEs. This shows up, for example, if you were doing a transpose of all of your data for something like an FFT. That would be exactly what you would use right there. There are also vector versions of these routines, which basically mean we don't have to be as regular in what we're sending out. We could have each one of the PEs send out, in the case of a scatter, for example, each one of the PEs can get a different count from some array. You might decide that you would like the first PE. So PE0 is broadcasting off this array, but it might want 2 elements to go to the first PE and 3 to go to the second and none to go to the third. So if you've got an irregular amount of data that you like to scatter or gather, the vector versions of these routines allow you to specify you give it a vector, you give it a count for each one of the PEs that are participating, how many elements you'd like to gather or scatter from them. So you can be very flexible with all these operations in distributing and gathering data, and you'll find yourself probably using at least the basic types at some point. There are advanced versions of this too. Again, I'm not going through the entire list and each one of these in detail. I'm just giving you some idea that if you find yourself asking, can I do something like do a reduce locally on data? Well, look in the documentation, do a quick scan through it before you start writing your own more primitive versions of these routines, because there are a lot of variations on these out there. So for example, if you do a min or a max reduction, you could actually ask for the location of the min and max. You don't have to go and sift for it for yourself. So do a scan through the documentation, the index. The routines are generally suggestively named, and the man page is often cross-referred to other related routines before you do write something that you think might exist, because MPI, again, and its many, many routines, has implemented a lot of this stuff for your convenience. Okay, so we won't drill into every one of these here, but we will move then on to communicators, which keep creeping up in all these routines that we're looking at. So far, we've been using the MPI COM World, our WorldCom communicator, because we've been using all of the PEs simultaneously for everything that we've done. As I mentioned, when I brought up communicators, this is often something that you don't want to do. You'd like to use subsets of the PEs, but since these collective routines that we're using, like barrier, for example, insist that all the PEs participate, you've got a real problem on your hand if you want to use barrier with some subset of the PEs. Because if you try to do that, it'll just hang because it's waiting for the non-participating PEs to participate. So this is where communicators now allow us to specify when we only want subsets of various collectives to work on things. And this will be critical for a lot of algorithms. This can also be very, very useful when we start looking at more complex or realistic topologies for our data decompositions. So instead of just a bunch of strips, we might want to have, again, a finite element code. You break things up into odd lumps or something like that. The communicators allow us to cope with that very well. Or if you write libraries, you can imagine that an MPI library that you're either writing or in all likelihood using, and there are wonderful MPI libraries out there to do a lot of things for you. You can integrate with your code. You'd like the library to be a black box that can go off and do its own thing. Well, anytime the library is using communicators, like say that the library author needs a barrier in there, well, if they need a barrier for the things that the library is often knowing as a black box, it'd be a problem if somehow you had to make sure that all of your PEs that aren't really using that library are also somehow participating in that barrier, so it doesn't become a problem. Well, we can, again, separate things and break off a pool of PEs to go their own way with the library using communicators. So let's look at how we do this. MPI has pretty much 2 ways of breaking communicators off. It has a group way, and then it has a way that's a little more explicit of just breaking off the PEs. They're both convenient and very straightforward. Let's take a look at that here with the groups, where we'd like to, in this case here, break off in a master-slave paradigm, we would like the slave PEs to be able to go off and do their own thing. So the master PE might be reading some input from the user. We'd like the slave PEs to go off and continue to do some number crunching or something. Well, we have a problem there then if the slave PEs want to do anything with the collective, because the master might not be participating. Here's the simplest possible example we could have, where in this case we want to do a reduce, but we'd like to do a reduce operation with just the slave PEs. And again, if we didn't have communicators, we'd have a problem of ever having a construct like we have here, saying if I'm not PE0, do this reduce operation. Without communicators, we'd have a problem because PE0 wouldn't participate in this reduce, which means the reduce would hang. The reduce would be sitting there waiting for PE0 to participate. But instead it works because at the communicator slot here, we have a communicator we've defined ourselves. We call it COM_slave here. How did we do that? Well, we used the group operations that are available in MPI to kind of shape together any group we want. And we group here. The first thing we do is we create a group from an existing communicator. Then we can use one of the list of group operations, and I'll give you a partial list on the next slide. But there's very intuitive things like, for example, one of them is called exclude. this allows us to exclude some PEs from the group. So we took our group that was all the PEs, and we're going to exclude one rank, and if we look up here, what we've set it to is equal to PE0. So in this, we exclude PE0, and now we've got a group that we're happy with. Now we turn into a communicator. So once you've finagled your group into the right form with the various group shaping routines, and you're happy with it, you can create a communicator from that group. And now you've got a communicator that anywhere in MPI where there's a communicator parameter, you can now use our defined communicator in place of the WorldCom. And that's what we do down here. So we can call reduce with just a slave PEs, and it works fine. And then right after that, we have a reduce that everybody participates in, and that's okay because it's outside of this conditional statement right here. All the PEs participate, and we have a different reduce here that also has PE0 participating in it. And when we're done with defining these things, theoretically, we should free them. In cases of groups, very often you're not doing it dynamically. This just lives at the very end of the code here. But you could create groups on the fly all the time and define new ones, and then in which case you should make sure you free them. So this is the way we do it with groups. There are a lot of group commands out there. To put together any kind of group you want, it should be very straightforward for you to create any group you can envision. We can also take an approach where we just work directly with the communicators themselves. We can forgo any of the group stuff here, and that is also commonly used in code. Here's an example right here. Very often, the most powerful routine to do this is the com split routine. You can see there are a handful of them that do things like duplicate a group, duplicate a communicator directly or something like that. The com split one is the one that you will see in a lot of codes because it in one fell swoop allows you to very quickly split PEs up into any kind of possible set of communicators that you might want. And the way it works is that all the PEs call this, it's a collective itself, all the PEs going into this call this, and they go in, each one of them with a color. It's what the MPI routines call a color. And the color determines, it's an integer basically, but it means that if all the PEs, let's say we have 100 PEs and they're all entering into this, they can each go in with an integer that says what communicator they're going to merge with, what group they'll belong to when they leave. So let's say with 100 PEs that we wanted to break them up into 10 groups from zero, the first 10 would be one group, the next 10 would be another group. We could say, okay, if you're less than 10, your color is 1. If you're between 10 and 19, your color is 2, and et cetera, et cetera. So if we called com split with that, what would emerge from that is each one of those subsets would now have their own communicator. We now have 10 independent communicators, and they could go off in 10 different directions and do their own things using these 10 different communicators. So com split allows you to do it in one fell swoop, break things up into any kind of subset you want. There's also a key parameter here too. That's in case you actually want to worry about within those when you create a new communicator, that communicator always has ranks labeled from 0 to whatever. So communicator ranks, communicator gives you a subset, but that subset always goes from 0 to however many elements in that subset. And so you can even specify when you split things up if you really want to specify what PEs have what numbers. So as we split our group of 100 up into 10 communicators, within each of those communicators we could even have each PE specify what new number it would like within that communicator. So you might have 10 communicators now, each numbered from 0 to 9, and you could specify that PE22 should have number 3 in its own little communicator. And there's also another number 3 for the PEs in the teens, for example. You might say that you want PE15 to be number 3 or 2 or whatever in its own subset. So you can get as detailed as you want, but very often the key we don't care about. You just want to split things into groups, and as long as they've got a number from 0 to whatever, you're happy. So we could replace what we just did in the previous example with a split instead. We could say, if I'm PE0, I want my color to be 0, else everybody else has color 1. Now when you split the communicator up, what happens after this is that PE0 has a communicator. It would actually be kind of inappropriately here called com slave, but it is a different communicator. Same variable name, but it's got a different value and a different communicator. So all the other PEs can now communicate with their com slave, which actually has its own value, and so the previous piece of code would work just fine. So there's 2 different ways that you'll see used to define communicators, and now let's look at some of the places where those communicators are really useful. One of the places that they're useful, again, besides just being able to branch off in your code, they're already useful for that. You can see if you want to branch off in your code and have some PEs do their own thing, they're not only useful, they're necessary. But here's where they can really come into some pretty elegant power with algorithms, where the topology that we're using to do our data decomposition can be aided a whole lot by the communicator. The communicator can kind of know about the way we've done a data decomposition and make life a lot easier for us instead of us having to do all the bookkeeping ourselves. So let's look at the two different types of topologies that MPI is happy working with. Cartesian topologies, in other words, a nice regular grid in however many dimensions, or some arbitrary graphical relationship between things. MPI's got some routines to work with both of these. Let's look at a nice Cartesian topology here and how MPI helps us with doing the bookkeeping. So here's a domain decomposition we've done on a metal plate, for example, and these are the, in this case here, the 15 PE or the 20 PEs that are involved. So there's 20 PEs that are broken up a metal plate here into a square grid. And we would like to capture this, well, we could do the bookkeeping ourselves. We could clearly create some data structures in memory that say this PE here is neighbors to the north, east, south, and west are whoever they are. And this, in many codes, is actually what people have done traditionally. They've done all the bookkeeping themselves. But it so happens MPI allows us to create a communicator here, in the case of the Cartesian communicator creation routine, that's very good at dealing with Cartesian grid layouts in however many dimensions you want. So when we create this communicator here called ComCart, we inform that creation routine about some things like the dimensions of our PE layout here, 5 by 4. We can tell if it's periodical or not, so you can have repeating boundary conditions or not. And then we create this communicator. So now we've got this communicator here called Com2D. And it now knows the layout of all of these PEs and how they relate to each other, and it can do some clever things for us. For example, it can tell us for any one of the PEs who our neighbors are. So we don't have to do the math and we don't have to keep track of it. At any point in time, one of our PEs can find out who its neighbors are in any particular direction with the Cartesian shift routine. And you give the communicator you just created to this routine, and you can say in a certain direction here, who are my neighbors, and however distant you'd like to look. So in this case here, if we do a Cartesian shift on this communicator we've just created, and we say we want to go in this direction here, it will tell us who our source and our destination are to send messages. So now when we do our MPI sends and receives, it's done all the calculations for us. It'll even do some clever things, like notice that if we want to do sends to our neighbors to the left, we can just say MPI send to the left, and it'll do it. It'll do a smart thing here, like know that this neighbor here to the left actually doesn't have a neighbor to the left, and it'll substitute for the destination in here this MPI proc null. It's a thing I pointed out yesterday, for example. It's kind of a predefined black hole you can always send a message to, and it'll be fine. It won't crash or anything. So it'll set up proc nulls for the neighbors to the left and the right and the top and the bottom for the PEs that don't really have neighbors. If they were repeating boundary conditions, it would actually know that instead of proc null, it should wrap around and send a message going to the left here, over to here. So the communicator now does this bookkeeping for us, and that can be a very nice thing in our code. So here are some of the other routines that you might want to use once you've created a Cartesian communicator to look and see things about who your neighbors are, who's in your plane. You might want to do things in a certain particular plane.
You have a question?
Yes, go ahead with your question.
Yeah. So how would you set up the periodic boundary conditions for the Cartesian thing?
To set up the periodic boundary conditions, we have a parameter here to Cartesian create, and we can set it either to true or false for each dimension. So this happens to be two-dimensional here. So if we set this to 1 instead of 0, it would say in the first dimension here, make this a periodic boundary condition. So periods allows you to set that up.
Cool, thanks.
Sure.
John, we have another question up here at Penn State.
Go right ahead, Penn State.
Okay. Can you ask it to send and receive messages to locations that fit certain dynamically determined criteria?
Dynamically determined. Well, you'd have to...
So say I do a calculation and I find a result, can I have it picked based upon criteria?
Well, of course, you can implement at the lower level if you want to implement your logic. Of course you can. I don't think that's probably your question. So you can at any point in time have any piece send a message to anywhere. So if you wanted to create any crazy logic you want to dynamically determine where a message goes, you can create yourself. How much? What you're probably asking is how much will these communicators help me with a situation like that? And the answer would be for something like that, you would have to create a new communicator that knows those destinations every time, every step that you do that. In that case, you might be better off just keeping your own routine off to the side that implements all of that logic. So if messages are heading in different directions every time step with a bunch of PEs, that would probably be the way you'd want to go. Now, on the other hand, the next thing I'm about to talk about, though, which is graph topologies, would allow you to deal with much more irregular communications, but even so, this kind of is assuming that they don't change one time step to the next. So if you do have a situation where you don't have any repeating patterns and things are going off in different directions, yeah, you're probably going to have to write that logic yourself. Yeah, MPI makes it very easy to do that, right? I can have a routine that calculates the destination, and it can be as funky as the logic needs to be. That's no problem, calculating a different destination for every message, every time step based on any parameters you'd like to roll into that logic. But the communicators won't, in that case, be the magic answer for you. But for cases where, the much more common case where you do have, static, at least, neighbors, so you might be sending differing numbers of messages. So that's not a bad question. So let me, as to how dynamic things are, so let me go back to maybe, for example, this slide here. So here's an example where we're sending, with the molecular dynamics example I said earlier, talking about user-defined data types. So in this case, for example, we're sending different size messages all the time, but our neighbors, our data decomposition isn't really changing, so we know who our neighbors are. So we do want, the communicator's great, it will tell us who our neighbors are and keep track of that for us, but the message sizes vary, but our neighbors aren't changing from one time step to the next. But something that's dynamic where they are. And by the way, that's not a far-fetched case. For example, one can imagine that if you're doing a weather code, I'll come back to the weather code because I think everybody understands it. Real weather codes, or a certain class of them, of useful weather codes, the grid that you break, your domain decomposition, is not static. It actually changes from one iteration to the next, because if we have something like a hurricane moving up the coast in our weather model, where you want a lot of elements in that code, or where there's huge pressure gradients, for example, where the weather's happening, where the action's happening, is where you want a lot of elements. You don't need so many elements and so much computational power out in the middle of the Midwest where nothing's happening and it's all boring. But where the hurricane's happening, you want a lot of processing power. So your grid, your domain decomposition to deal with that problem would probably have this grid that has a lot of elements there, and when you break up a grid, you'd like each PE to have the same number of elements roughly, so your PE distribution is going to be very irregular, but, and this is the key point here to address this question, it's going to change from one time step to the next. As that hurricane moves up the coast, your domain decomposition isn't going to stay the same, it's going to evolve. So a dynamic adaptive mesh like that would require every so many time steps, maybe every time step. Very often you try to do it every minimal number of rearrangements because that rearrangement is expensive. But every so often you create a new mesh and a new grid and a new arrangement of neighbors. So that question is not rooted in some exotic case that you're never going to come across. It does happen in dynamic meshing cases that you do recreate your domain decomposition on the fly as the problem evolves. And in those cases, you might find that a graph topology is actually more appropriate than a Cartesian topology. So a graph topology allows us to define any arbitrary list of neighbors. It doesn't just assume a grid layout. It might even be useful in a fairly grid layout, because if we've got something like an FEA code, even if we have a grid section of that code, we might care about, say, our diagonal neighbors, and it might be a good way to capture that. But at any rate, as soon as I say graph topologies, people immediately think of something that's just an arbitrary layout. And that's fine, because MPI does, with graph topologies, allow you to define any arbitrary bunch of neighbors for any given PEs. There are two sets of those. Well, there's actually three. There's the original old one from MPI 1 that we won't worry about, because the newer ones, by newer I mean they're still 20 years old, are much better. And they are an adjacent graph interface and a general graph interface. One that allows us, if each one of the PEs knows who its neighbors are, this is one way to define it. Sometimes you only have some special PEs that calculate the whole layout and distribution, and so they need to tell the PEs who their neighbors are, and that's the general graph interface. So let's look at the adjacent graph interface. It's very straightforward. It's just each PE that participates in creating this communicator here knows who its neighbors are. And it has degrees, say how many neighbors they have. So for example, for PE 0 here, has one neighbor that's going into it and one neighbor that's going out. So if we look at its in degree as 1 and its out degree as 1, and then you list who the PEs are, the two neighbors. And so whenever so it's very straightforward. So you give it a list, each PE gives a list of who its neighbors are, and then they call the communicator create, and now there's a communicator that knows about this relationship and knows who the neighbors are for each PE. Can also get, if you look at all the parameters here, we could also even add in weights here that maybe say what the strength of these connections are. That's a little bit more subtle of a thing, and it's not always guaranteed to give you a great optimized graph and everything. It's a difficult problem. But at any rate, it's very straightforward with graph topologies to put any kind of neighbor relationship together that you want. The general interface, as I said, is the case where the PEs don't know who all their neighbors are, but some of the PEs might. So in this case here, we have PE0 actually listing the neighbors for the other PEs. PE0 and PE4 here, between the two of them, create the neighbors for the other PEs. PEs 1, 2, and 3 here don't know anything about who their neighbors should be. So that's the general graph interface. So you can use either one of those. Now you've got a communicator that knows these relationships. So how is that really useful? It's really neat now in that we have routines that allow us to do things, well, in this case here, just find out who our neighbors are. So these allow you to find out after you've created this communicator who all of your neighbors are. So that's nice. That allows you to figure out maybe where you should send some messages and whatnot, and can be essential. But more importantly, there are some routines that when you give them these neighbor communicators, these graph communicators, do some pretty magical stuff in terms of bookkeeping here. So for example, all gather, neighbor all gather, and neighbor all to all do a really good job in one routine exchanging information between all the neighbors in this graphic communicator. So once we've set up this communicator, if we call neighbor all to all, for example, this is like doing a broadcast, or excuse me, all gather. This will exchange information with all of our neighbors that are near us and just near us for each one of the PEs. So it's doing a broadcast, in other words, just to your local neighbors. But they all do this simultaneously. So this way, picture you've got these graphical relationships set up on your finite element mesh, for example, all across your machine. We've got a million PEs here with these complex finite element mesh built up. And we just want to exchange information with our nearest neighbors because, as an emerging theme here has been, right, that in MPI and data decompositions, it reflects the physics of you often just want to talk to your local neighbors, right, whether it's our weather code or an FEA code where the stresses and strains are really your local neighbors. So we just want to exchange information with our local neighbors. We'd like all of the PEs to do it all at once, and we would like to not have to worry about exactly who our local neighbors are because it's this mesh relationship that's captured in our graph. Well, in one swoop here, this will do that. It will exchange it will broadcast to all of your local neighbors some information. All to all does the same thing, except it's exchanging with our local neighbors. So in this way, we can send and receive from our local neighbors a buffer along the edge. So this is kind of like what we do with our weather code, to send and exchange information along our borders with our neighbors, except this is where we get to define what our relationships are, as we probably would with our states in terms of a graph. Some states have 4 neighbors and some states have 6 neighbors, and we can define all that in our graph, put our communicator together, and then the only place in our code that we do all of our data exchange is this neighbor all to all. And in one fell swoop, in one routine, we exchange simultaneously, everybody exchanges just with their neighbors. Whether they have 4 neighbors, whether they have 6 neighbors, all of that stuff that bookkeeping is rolled into this routine right here. So this is pretty nifty stuff. Again, it's nothing you couldn't implement yourself with your own bookkeeping, just doing sends and receives. It's kind of nice that it's built in, and once again, also is probably more efficient than anything you're going to write yourself because it gives the system the opportunity in the background to set up this stuff and do it in one fell swoop. And also, again, also rolls in nifty stuff like knowing that if there are proc null PEs, in there that don't have neighbors or whatever, it deals with all that automatically. There are some more of them that allow us to do even more flexible stuff. If you wanted to send different size chunks of data to different neighbors, there are vector versions of these routines. So you're going to have a hard time coming up with some message pattern that you're not going to be able to capture here with this. And again, as I've mentioned several times here, these weird domain decompositions where you've broken up a mesh and a regular mesh into a bunch of chunks like this are not in the least bit uncommon. This shows up in the real world. Virtually any finite element code, for example, this is the way you break things up. This happens to be a project I worked on, which is seismic modeling. So we took the geology of an area. We're trying to model seismic waves going through an area. We take the geology of the area and you break it up knowing that some areas are denser and some are less dense. And so you don't want to have a regular grid. You'd like to have more grid points where you need them and fewer where you don't. And you end up with an irregular mesh. And then you've got this irregular mesh. Well, now you'd like to make sure that each one of the PEs has roughly the same number of points to work on, because otherwise you end up with a load imbalance. And we'll come back to this topic at the end of today, but a load imbalance is a good way to make your code run slow and inefficient if some PEs have a lot more to worry about than others. If one single PE in our weather map is responsible for Texas, and one single PE is responsible for Rhode Island, we've got a load imbalance. One PE's got a lot more work to do than the other one. That's going to drag everybody else down. So what instead we'd like to do is we really want to break our weather map up into PEs have the same number of points. And in a finite element code, when you do that, you end up with some very irregular shapes, and that's fine. MPI has, you could do your own bookkeeping on all this stuff, and some older codes do, but if you'd like to, MPI will help you in keeping track of who your neighbors are and make it easy to send and receive data. Okay, we'll skip this here. It's not that interesting, and jump into something that is very interesting. But before I leave communicators, I'll mention once again that they're a convenience thing at times, but all of your collective operations are built around communicators. So anywhere you've got a collective operation, if you don't want to use the world's communicator, all the PEs doing exactly the same thing, then you're going to have to define your own communicators to break things off into separate pieces. Okay, let's jump into the second topic here. Not second topic, second major topic I think of it as, which is where we could spend a lot of time, but I'm gonna force myself to go at a fast pace here. Please slow me down if you have questions. And that's the whole area of MPI having a nice evolutionary path to go from the simple blocking sends and receives that we've got into some very optimized, but you take more responsibility for it, single-sided message passing, things that make it a little bit more efficient. What do I mean by single-sided? Well, our default MPI message passing, which we went into yesterday into some detail, says that if you're going to send this array from PE0 to PE1, it actually ends up going through this intermediate process. It gets copied down to here, and then it gets into a receive buffer over here until the receive is called over here. So there's some copying going on. And it might even have to be sliced up if it's a really huge message and can't fit into these buffers. But at any rate, there's some stuff going on in the background, and you might imagine that this is a little bit costly. It's got to make copies of things, and our data is usually big chunk. Our messages in real MPI programs are often substantial, so there's copying going on. We might want to speed things up a little bit. Also, we got that deadlock problem we mentioned. If these things are so huge that they have to be sliced up, they can end up backing up here. And if they back up on both ends, you end up with a deadlock. So non-blocking message passing solves that problem and buys us better performance. Without great cost here. We'll see that it doesn't cause us to have to do a whole lot more logic in our code. So here is our example of a deadlock with two PEs sending each other. PE0 and PE1 are both trying to send each other a message and then receive a message. And if the messages are small, this works just fine. But if the messages are huge, we'd get a deadlock. So in our Laplace code, for example, we might have something that's like this going on, and everybody starts trying to send to the left, and then they all get stuck before they can send to the right. So if we write our code with everybody send, everybody receive, we can potentially run into this problem. So we don't want to do that. What we'd like to do to avoid this, we might write our code so everybody sends to the left, and then everybody receives, and everybody receives from the right. But even this isn't a really good solution, because what ends up happening is everybody sends to the left, but they still have to wait until PE0 at least can unbreak this logjam here, because PE0, since it didn't send to the left, can at least receive a message. So it unbreaks the logjam and keeps this stuff from happening. But and now the messages can kind of flow back this way. But you can see even this, even though PE0 broke this logjam and prevented a deadlock, it caused things to kind of serialize some. Things couldn't get exchanged simultaneously and quickly. So we can do a lot better than this by not having to worry about any deadlocks or anything else by using non-blocking routines. So we'll spend a little bit of time here talking about the non-blocking routines, because you'll doubtless find them to be helpful. But I'll point out that there is a particular MPI routine that solves this particular problem, just in case you stumble across it and say, why didn't John mention send or receive? Because this is such a regular pattern of exchanging with neighbors, there's an MPI routine called send to receive that does exactly this. It exchanges with your neighbors, and it'll avoid deadlocks. So you can use the MPI send to receive routine. You could stick this right now in your Laplace code solution. it'll be a drop-in, right? And it'll work right away and allow you to exchange with your neighbors, send and receive at the same time. So this is a nice routine that's out there, that's convenient, because so often that's all you do want to do is just exchange directly with your neighbors. But the more general solution, the thing we really want to talk about, are the non-blocking routines here, because we never have to worry about deadlocks then, and they also buy us a lot of performance. They avoid these copies and buffering and everything that goes on, if possible. And all they are is the sends and receives we've already been using, but they have this little flag stuck on the end that allows us to tell when they actually complete, when they're done. So it looks like sends and receives, but they're called I send and I receive here. So they're otherwise the parameters are the same. It's just you point at a buffer and you tell it how many of whatever you want to send, and you give it a destination and a tag and whatnot. So it just looks like a normal send or a normal receive. The difference is these will always return immediately. It doesn't matter how large your message is, it will return immediately, even if it hasn't had an opportunity to send it yet, if it's still sitting there in memory. And the receive, doesn't matter that your matching receive hasn't received anything, it'll come back immediately. There's no data in here yet, perhaps, if it returns immediately, but it will never wait, it'll never block, so you can go off and do other things. Well, how do you know when it's safe to either modify that data that you think you've sent, go back and continue to work on it, or how do you know when the message actually came in so you can start to use that data to do something? And the answer is that we can test these request flags to see if the operation is completed, or we can just sit there and wait for it. So we can test or we can wait to see when these things complete. So they're non-blocking, they'll never block, neither the send nor the receive, but we have a little bit more responsibility now. We've got to go and make sure that things have completed. So we have a nice handful of routines here to allow us to wait on some or any list of messages that we've got out there, outstanding, and some variations. Let's look at how easily this goes into our code. So we have our shifter code, which we did with blocking routines previously, sends and receives. Here's how we could do it with non-blocking routines, is that instead of using I send and I receive, we just put in I receive and I send here. So in this case here, each PE says I want to receive a message and I want to send a message, and I've intentionally kind of put them in what you might think is a non-intuitive order, because it doesn't matter whether I try to receive or send. It doesn't matter because they're non-blocking. It just says someday I'm going to expect to receive a message from somebody, and by the way, here I want to send a message. So these are the non-blocking sends and receives, and we've implemented them here just like a normal send and receive. The difference is that at the end, the last parameter here, we give it a pointer to where we're going to keep these flags that tell us, these request flags that tell us when the operations have completed. So when flag 0 is done, we know our receive has actually happened. We've got some data that we should look at. And when flag 1 is filled in right here, becomes true, it means that our send has completed and we could go and mess with whatever data we sent. So we've done these here. Here is where we could go ahead, where I've got this comment statement. We could do any work that we wanted, as long as we're not messing with our send buffer or trying to use our receive buffer. We could do other work. This is one way that in MPI you can overlap computation and communication. That's something that's pretty desirable, is to be able to, while we're waiting for our message passing to take place, which can be, for a lot of codes, that sending data communication time can be substantial. While that's going on, it would be ideal if we could do some computation. Non-blocking sends and receives enable that to happen, because as long as you got something to work on, we don't care about the sends and receives going on in the background. So we could do something interesting here. We choose not to in this simple shifter example. Instead, we're just going to wait until these two flags, so we tell it how many we would wait for. We're going to wait until all of our flags are done. So we say, okay, wait on all the flags to become true, and then continue on. So this wait right here makes sure that the sends and the receives up here are complete before it tries to print out the value. So it's our shifter routine, but it's non-blocking. Means it could work theoretically with any size messages. It'll never deadlock. And you can see there isn't a whole lot more logic that we had to do. We didn't have to change our code a whole lot, but there is a little bit more. We're a little bit more responsible for making sure that we wait before we go ahead and use or modify our data. And there are some variations of this that make life even more convenient and elegant in our code. So, for example, our Summer Bootcamp Hybrid Challenge winner, something I'll talk about in a little bit at the end of today. It's a competition we have in our Summer Bootcamp where programmers take our Laplace code this year and try to speed it up as much as possible. And one of the winners, or the winner from 2 years ago, went and use the send init and receive init variations on this. So these are some nice variations that you'll find out there in the index that'll say if I'm going to do repeated messages in the same pattern like we do in our Laplace code, I can set them up once up top here. Say these are my neighbors that I'm sending to, left and right here. So these are my neighbors. Let's set this stuff up, initialize this stuff here, and then anywhere that I actually do my message passing, all I need to do is start them and then wait on them. So this is a nice way of breaking out all the setup for our routines up here. Everything's set up right now. We know who our neighbors are. And now down here, we can do non-blocking message passing. It triggers all the communication phase of our code right here in our Laplace code. And then it goes ahead and does some stuff. In this case, it does those copies between our temperature array and our temperature last array. Those actually take a little bit of time. So while the messages are being passed around, it's going ahead and doing that copy over there. And it's fine because copying these two arrays between each other doesn't need any of that data. And it says, okay, you're done with that. Well, now make sure that before we go back to the next iteration of loop and start to do it, the calculation of the next iteration, make sure that at least the messages were sent and received. And that's what this wait down here does. So you can see the code is pretty clean. It's a nice tight little piece of code here. It performs well consequently because of that. And at the same time, it's non-blocking sends and receives. The logic isn't all that complicated or anything. And maybe the most important point here is that this was a nice evolution from the blocking sends and receives that you're probably using right now to do your solution. So whoever did this didn't go, oh, I wish I would have used non-blocking sends and receives. Instead, they went back and turned it into non-blocking sends and receives with a little bit of editing. So nice thing about these MPI, and I'm going to go into even some more high-performance versions of message passing here. And the whole time, I hope you'll notice that these are things that you can incrementally add to your code. You don't have to go back and refactor everything. We can mix and match if we want blocking and non-blocking if you care. You could do blocking, non-blocking sends here and blocking receives. That's just fine. That works fine. There are a bunch of non-blocking routines in the language that most of them have this I version in front of them. So, we've got instead of send and receive, we've got I send and I receive. We have even a non-blocking barrier. This is one that usually catches people off guard. What is a non-blocking barrier? Does that even make sense? It actually kind of does. A non-blocking barrier we can stick in our code, and it won't actually block any of the PEs, but the flag will become true when all the PEs have gotten to the barrier and gone past it. So it's one way you can check to see if all the PEs have gotten past the point without making them waste time at the barrier. Barriers in code are kind of undesirable in the sense that it means PEs are sitting around doing nothing. It's wasted time. They're inevitable in certain cases, right, if you want to get the correct answer, so you don't just stick them in for no reason. But sometimes you just need to make sure all the PEs are past a certain point before you go do something, but you'd like them to be able to not just hang around. Non-blocking barrier does that, as odd as that sounds. Okay, let's take a look at the next stage of optimization that you could go with MPI, which is single-sided message passing, which is where we have the message, the responsibility for doing all the message passing is only on one end. We don't have a matching send and receive. Instead, we just push the message straight into memory, or we grab some data straight from memory, and that avoids some of this copying here that we have going on here into our send buffers and our receive buffers. So single-sided communications are a performance win. They avoid some of this copying here, and they can also make your algorithm a little bit easier to implement. They can just clean up your code, actually. Again, it can be a win from the elegance perspective as well as the performance perspective. And the most common versions of these are the put and get routines in MPI. And they're lovely. They allow us to say, okay, what I really want to do at the end of the day is get this array from here to here. I don't really care about all this other stuff that's going on that message passing does. I just want to put this thing in memory there. So can I have a routine just called put? It just jams it right into the memory over there. And the answer is yes, you can. But there are a few considerations that you have to deal with in MPI. You have to define some data windows, some places in memory where this stuff is allowed to happen. MPI doesn't allow any PE to just go anywhere in the other PE's memory and do things. Instead, it says we've got to define the windows that this is allowed to happen. So you basically give it a list of variables in memory, array locations in memory typically, that are allowed to be remotely accessed. Then you move the data. But we've got a problem here. If we do this kind of put thing, how does this PE know that the data, the new fresh data that it wants to use, how does it know that it's there, that it's arrived, that it can do its next time step? And the answer is we need some kind of way to know when that's happened, and we'll see what that is, some fences here. So here's our PI code done with single-sided communication. I took the previous version of the PI code that we had with blocking sends and receives and broadcasts and whatnot, and said, okay, if we want to do this with single-sided communication, we can have the other PEs go to PE0. PE0 here is still going to get from the user the number of slices as input, and it's still going to collect the answer at the end, but we'll have PE0's memory just be accessed by the other PEs to get how many intervals there are. PE0 won't worry about sending messages. They'll just go in and grab it. And when they're done and they've got their partial sums of pi that they've done, they'll just go and stick that answer back in there. And this is what we do. But we need to create some windows to allow that to happen. And WinCreate is how we do that. So the window create routines are collectives. That means all the PEs have to call them, not just the PE that you think you're messing with its memory. All the PEs have to synchronize on what the windows are. In this case here, PE0 is going to create a window. It's a very small one here. It's only got a couple variables. It's got the end variable, the number of intervals the user enters, and it's got the final result variable. Very often these will obviously be large arrays or sections of arrays, but in this case our windows are just two variables. The other PEs, because it's collective, need to call the routine as well, so they call this even though they're not creating any windows locally, so they don't have anything, they're not really creating any windows, but they are kind of acknowledging that PE0 is going to windows. So at this point now, we've set up these windows so that we can use the collective, the single-sided communications here. So we jump into the logic that we had before. PE0 reads in a number of intervals from the user, and now the other PEs need to find that out. They do that with a get statement. They just go straight into the memory of PE0 and they get that value directly from it. So there's no mutual exchange of data here. However, as I mentioned, how do they know when it's time to go and get that data? And the way that we synchronize things to know when it's valid to go and get data are with fences. So we have these fence commands here that say, at this point right here, PE0 has completed reading in from the user this data. A fence command you can think of as a barrier, basically, so that says when it's valid to do some operation. And fences, because of this, will typically separate the computation phase and the communication phase in your code. And that's exactly what has emerged here. So here's a little data I/O phase, and here's a fence for communication. So fences off communication is probably the simplest way to put it. So we fenced off the communication here, then here's the communication. They go and get from PE0 this. Then we fence it off before we go on to the next step here to make sure that they've all had a chance to get this before we move on to the computation phase. Now they all compute things. Now before we go on to the communication phase, again, we fence things off. It says, okay, everybody's done computing here. Now we can go and put all the results, the reduce operation, back into PE0. But for various reasons, reduce operations in single-sided communication are called accumulate. This basically means we're accumulating into one location some results. It's basically the exact same thing as previously we had a reduce sum. This is just an accumulate sum. So it's exactly, just think of accumulate. Whenever you see accumulate in MPI single-sided routines, think reduce. So we've got a reduce sum operation here. It's where we add up all the pi. So each one of the other PEs goes and sticks its partial sum back into PE0 here, but they don't overwrite each other. They accumulate the result together. And now we've got the result. How do we know when they've all finished that? Well, we have this fence command. Now PE0 can print out the answer. So we've turned our finding pi routine from yesterday with blocking communications into single-sided communications. Not a huge win with this particular code, but it's a very clear illustration of how easy it is to go to single-sided communication. To create windows is generally a matter of just pointing out your variables. You might have the additional complication that, again, in real codes, your variables are dynamically sized and allocated. So if you have dynamic allocation of memory, there's a few more details you need to worry about to make sure that you can point that each one of the windows is created at the right place for your dynamic memory allocation. No big deal. When we have these things set up and ready to go, we do most of our data movement with puts, gets, and accumulates, which do exactly what you'd think. We'd say we want to put some data into a remote PE. We'd like to grab some data from a remote PE, or we'd like to do a reduce type operation with a remote PE. There are also non-blocking versions of these that kind of, if you want to think of it, that they're always non-blocking, but they give flags back and tell us when things are complete as well. So the same kind of flags that we have in our non-blocking routines. The win fence command, just think of it as a barrier to separate the communication section of your code out. It's a little more subtle. If you really wanted to be, this is a little bit overly cautious. We could actually even try to overlap a little bit of some stuff if we wanted to get fancy. So if you want to dig into this a little bit further, you could violate this rule. But if you stick to this rule, you'll always be fine. Just separate the communications and the computation of your code with fences. Okay, so that's what I'm just illustrating here. The fences just separate the communication part of the code. However, so far, what we've done is not entirely single-sided in the sense we still have these fence commands that we need to separate things with. And you can think of algorithms, and there are cases where that's inconvenient. We would just like things to happen in the background, and we don't need PEs to have to worry about when things have completed or not. There are other ways that they might figure that out. And so we can do completely passive RMA, single-sided communication, where we define the windows again. You have to define the windows that other PEs can access, but then the participating PEs that maybe it's getting something put into its memory never calls anything like fence. Things just appear in its memory, and we have to determine with some other method, when that stuff's valid and when we want to access it. But this allows us to be completely passive. So we can do that. We set up these windows that we can lock and unlock on a target PE. So the remote PE can set up a window, lock that window, stick some data in there, and unlock that window, and that target PE doesn't participate at all. It's completely out of the loop. So this is kind of the more single-sided way of doing things in a sense. And so we have routines that allow us to do that with what MPI calls passive RMA. Once again, we define and we can allocate dynamically even these windows, and we could use this to set up something like, here for example, is a counter. Maybe we've got our MPI code reading and processing values, and once in a while it encounters an error value, an anomalous data, maybe some bad value in a file that we expect to have, and we'd like to have a global counter sitting in a PE. PE0, for example, has a global counter of bad reads bad data that the other PEs have encountered. So you'd like this counter to be sitting in memory, and it gets incremented every once in a while as bad data gets encountered. If we try to implement this with our old send and receive type routines, you'd think about it, PE0's got this keeping track of this counter, but in order to do that, since the messages are random, it could come in, doesn't know that there are any messages, or how many there are, or where they're coming from, the only alternative we'd have is to sit there in a loop, always trying to receive messages to see if something's going to come in to increment that counter. That would be kind of wasteful. All we'd do is sit there and pull all the time. Instead, we know with single-sided communication, we might hope that we could just stick directly into that counter in PE0, stick an incremented value of error. So PE212 finds an error and it wants to increment that counter in PE0. It can do that without PE0 having to sit there and wait for messages all day. We can just use single-sided to go right into memory and cram it in there. And that's exactly what we can do with some code like this. We go to PE0, we lock its memory in that region where we want to increment the counter. We increment the counter. The accumulate command allows us to accumulate. It's again like a reduce operation. So we're going to add 1 to that counter and then we can unlock that counter. So that's great. However, this does introduce one of the subtleties of parallel programming, which is the possibility for race conditions when you've got a lot of PEs accessing one location out there in memory, because if PE0's counter is set equal to 100, it's found 100 errors so far, been accumulated with all the other PEs, and I'm PE212 and I found a new error, what I would naively do would be go to PE0 and find out its value of 100, and then add 1 to it, and write back 101. But that process actually takes time. I have to go there and read 100. So I go there and get 100 to bring back to add 1 to. In the process of that happening, some other PE could go there and grab that value too of 100 because it found an error. So we both grabbed 100. I added 1 to it. This other PE added 1 to it, and we both write back the value of 101 then instead of 102, which is what we should have had happen. And this is a race condition, and it's an easy enough thing to trip off into when you have simultaneous access of shared variables in any kind of parallel programming. And so the standard way to deal with these kind of problems is to have routines that are aware of the fact that these kind of possibilities can happen, and we have that in MPI with the fetch and op command. And this makes the operation atomic, as it were. It makes it happen in one step instead of allowing the possibility that somebody else can simultaneously be trying to access that data value. And so we have a bunch of routines to do that. So for those of you that are thinking about implementing, for those of you that have experience in parallel programming and are thinking about having a bunch of single-sided operations, distributed memory, are there possibilities of race conditions happening? The answer is yes, and the answer is we also have the tools that allow us to deal with that in the standard concurrent programming fashion. And many of you will never wander stray into this territory, but if you start hearing words like, mutex, and things like that you're trying to implement globally, the tools are there to deal with it. I won't go into all the similar routines that allow us to deal with those situations, but they're there. There's one last approach even. As I said, MPI has this nice ladder of ways that you can incrementally optimize things depending on your situation. There's one that probably only compiler writers mostly care about. People write compilers for parallel programming languages in MPI. In particular, things like the PGAS languages that people are really hopeful will make life at massive scale easier than having to use MPI. Co-array Fortran, which is now part of the Fortran 2008 standard, UPC. People hope that are writing parallel languages that work across thousands of cores. They inevitably are built on MPI. So MPI is really the layer everything functions at. So people writing parallel compilers build them on MPI. Those people, for example, are concerned about having an array that's distributed across all of memory. And so the nice thing about this language is, as an MPI programmer, when we distribute an array across memory, like we did in our Laplace code, or we're doing in our Laplace code, we had to break it up for real into pieces. We no longer have a 1,000 by 1,000 array. We had to break it up into 4 250 by 1,000 pieces. One of the ways that these parallel programming languages hope to do it is you can just keep your 1,000 by 1,000 array and you program like it's still there. And behind the scenes, UPC or co-array Fortran will worry about the pieces being broken up. And they use MPI behind the scenes. They basically implement what we're doing for you, is the hope. So somebody writing a compiler like that might even, in a quest for the ultimate optimization, might actually use this last kind of scalable synchronization RMA, which is something that was added into MPI with 3.0 to enable these kind of compilers. And it basically it's basically set up around just nearest neighbor communication only to avoid any extraneous communication, and it's single-sided as well. And so it's similar to the single-sided stuff we're just talking about, but is meant to work at exascale with millions of cores and only communicate within the closest neighborhood, within the communicators that are just the closest neighborhood, so there's no extraneous communication. But it's, again, the same kind of RMA stuff. So I won't go into great detail with that. Most of you will never care about it. But it's the last piece of this kind of ladder that you can go down, where you could start developing an algorithm with blocking message passing. And as long as your message sizes aren't huge, it's going to be just fine. It's going to be a friendly way to get your algorithm up and going, your code up and going. At some point, you may decide that you may expose yourself to say something like a deadlock, because the data is so huge that it could possibly deadlock. And you can switch to non-blocking message passing very easily. As a matter of fact, experienced MPI programmers just generally maybe just implement things in non-blocking message passing right off, because why not? It's simple and friendly enough. So you might find yourself just writing in non-blocking message passing, but you'd never regret because you made the wrong choice here. And then going to single-sided communications can be both algorithmically simple, but certainly an optimization. It avoids even more of copying stuff around. And you can implement anywhere you want on this ladder, and you could change it up. You can have some routines that are, you've implemented as blocking message passing because it's just some initialization stuff and it's lightweight and nobody cares about its performance. And the real kernel of your code where the number crunching is happening, you could do with single-sided communication. So you can mix and match these, and you can evolve them as you go, and that's a wonderful thing. It means you don't have to worry you made the wrong decision when you've started your coding out. But they're compatible, mix and matchable, and you shouldn't hesitate. Like I said, a lot of programmers just will start out with non-blocking message passing. Shouldn't hesitate with the Laplace code, for example, to experiment with some of these. Okay. We'll jump now quickly through a variety of things I want to give briefer mention to, which are things like hybrid programming. I can't really dive into hybrid programming, which is mixing and matching MPI with some other parallel programming approaches, in particular GPU programming or multi-threaded programming. I can't jump into this because I can't assume any of these other programming approaches. The only time I can is our summer boot camp, when we teach all of this together and mix and match. It's a wonderful thing for me because I finally can meaningfully talk about how to mix these. But for those of you that do or are interested in it, you should be aware of the fact that MPI is wonderfully compatible with OpenMP and with OpenACC because they have to be. Everybody has to work with MPI if they want to be seriously useful. So here's the most complicated version of mixing OpenMP and MPI, where every OpenMP thread, so OpenMP is used to program multi-threaded codes just on individual cores. We talked about this yesterday, of a single node. So if I've got an OpenMP algorithm and it works just on a single node, and now I would like those to scale that up to work on multiple nodes with MPI, I could have each one of those cores sending its own messages back and forth with other cores and other nodes, and it will work just fine. Here's an example of where that happens. Here's an OpenMP parallelized loop, and each one of the threads in that loop is sending its own messages back and forth with other threads, and here you go, is the output for it. So any of you that are interested in this particular topic, I'd be glad to talk about it in as much detail as you'd like. Dynamic process management is something else that initially seems more interesting than it turns out to be. This is the ability to start and stop new MPI processes in the middle of a job. So far, all of our codes, we start them with MPI run and we say we're running on 8, we're running on 4, and we assume that for the lifetime of that particular run, that's how many PEs we have. That's a pretty reasonable assumption. However, MPI does potentially have the flexibility to say, I started on 4 PEs, but I'd like to grab some more. Or I started on 100, but I'm going to give some back to the pool. So you can potentially dynamically size an MPI run as it's happening. Turns out that the complexity of that, and the more important part, the undesirability of the batch system or an operating system to allow you to dynamically resize your processes is something that means nobody implements, nobody allows this kind of MPI mode on their system. So even though it was added in way back when with some excitement, there was some notion that work sharing that would change the dynamic pool size of jobs and everything would be popular. It ends up being just something that people don't want to allow. When I say people, I mean everybody from the operating system writers, the schedulers, the system administrators, just aren't happy about your job suddenly deciding to get a lot bigger in the middle of a run. So nobody enables this stuff. It's just not practical. So you won't actually see this in many codes or any codes. But it's technically there. MPIO is the other thing that falls in this category of the enthusiasm sometimes gets ahead of the reality. I/O, as mentioned, is an important part of many codes, and scaling your code up doesn't make the I/O go away. It usually aggravates the situation. We've got a lot more data. Our code's so fabulously fast, it's number crunching faster than ever. It eats data faster than ever and outputs it faster than ever. So parallel I/O is important. Because it's important and because it takes a little bit of thought, MPI as a version 2 rolled in something called MPI/IO, a bunch of routines to allow you to build on the collectives that you've got and the data types that you've defined to do nifty things like say, hey, take this distributed array, take our Laplace array that's really distributed in memory and no longer exists, and write it back to disk as a single array. So spit it out to a file and reconstruct that 1,000 by 1,000 array. And it can do nifty things like that. The only problem is the performance is sometimes very disappointing, is often disappointing. And the reason is that real parallel I/O has a very platform-specific character to it that can be make it difficult to write a generic approach to I/O. That's the bad news. The good news is it's easy to overcome that, but MPIO is not the answer. Typical parallel file system might try to do an operation like this. All of our PEs simultaneously want to write back to a single file. So they're all writing data to some subsection of the single file that's sitting out there on disk. Probably a parallel file system, something like Lustre on Bridges or GPFS. So you've probably got a shared file system, and all the PEs want to write back their partial. It's the weather code. They don't like to write out their particular step of the weather so that it could be rendered and passed along. So all the PEs want to write their particular state of weather. So PE wants Pennsylvania wants to write, and Ohio wants to write, and Nebraska wants to write to the file of the weather map at the same time. In reality, behind the scenes, what parallel file systems look like is something like this. A lot of the PEs share some intermediate point. Something with Lustre, it's this thing called an OST. It's usually some kind of metadata server that helps to coordinate and access to the data. So between your PEs writing to this shared file out there and them actually getting to the file, there are choke points. And these choke points can very, very quickly become the bottleneck that slows your data writing down. So you generally don't want all of your PEs to simultaneously be certainly writing to a file. Reading might not be as bad, but it's not sometimes great either. But writing to a file simultaneously from all the PEs is going to be a terrible idea. It'll overwhelm the file system and oftentimes just bring it to its knees. So you don't want to do that. Fortunately, MPI allows you individually to implement things. MPIO, by the way, tries to step in between and magically manage this. It says, if you use MPIO, I'll try to do this. And it usually fails because these particulars of this right here are very, well, particular to your local implementation, your platform. So it's hard to do this generically. MPIO, this is where it fails, and then you're kind of out of luck because how do I adjust it? Instead, what's usually a very pragmatic, effective solution to this problem is that your I/O routine in your code, which generally is already its own separate routine somewhere. It's a nice thing. I/O in a code is usually, here's where we write disk, here's where we checkpoint to disk or whatever. Where that routine is, with some simple MPI, you can do what's usually very effective, which is to say, hey, let's collect from all the PEs the data, one PE, and have one PE, well, not one PE, but have a subset of a pool of PEs grow together and have each PE. Trying to think, let me rephrase. The diagram is very clear. My phrasing of this isn't correct. Let's have a subset of PEs be responsible for writing all the files to disk. So their neighbors send the data to them, and they write to disk one at a time. So if we've got 1,000 PEs, maybe 10 of them are responsible for writing the disk file out, and we use standard message passing to send the data to them, and they write to disk. Now our 10 PEs aren't overwhelming the file system. We can get nearly the optimal performance out of a parallel file system, which can be very good. So we can get this fantastic bandwidth without overwhelming the file system, and it's not hard usually to write some code that does this. It's usually dozens of, a couple dozen lines of code, and you've got it. And the nifty thing is now we've solved the main platform independence problem, which is that you put a little slider in your code. You basically have a parameter that it says, how many streams do we want to write on our file system? So our departmental cluster, we might recognize we only want to write 5 streams. On big resource, national resource like Blue Waters or something, we might want this to be 500 streams. But you can tune it, you can set a parameter in your code that's very easy to change, isn't complicated logic, and now you can get some very, very good file I/O performance. That's the reality, and that's pretty much what I encourage people to do, and it's a fix that I've gone and implemented in more than a few codes over the years where people have terrible, dismal I/O performance. So it's easy to do an MPI, but the bad news is that the MPI/I/O stuff that's just sitting out there tempting you to use it is not typically the solution. So it's a little naive to just use MPI/I/O and hope for good results. It can often be the opposite, and then it's a little tricky. Okay, there are a bunch of other things I'm going to even more quickly whip through here just to be aware of. Let's see. MPI 3 has attributes, so if you can add the communicators and data types and windows and stuff, little whatever. Essentially it's got a key value database attached to these things, so you can, if you're writing libraries and things that's neat, you can attach attributes, characteristics to all of these things. That's not widely used. Fortran 90 has the ability, and I hope any of you using Fortran write at least Fortran 90 style code. I mean, hey, we're up to Fortran 2008 standard here, so I hope you at least use array shaping and slicing frequently in your code. It's crazy not to. I still see old style code getting written. So if you're using Fortran 90, you might think that a good thing to do, a logical thing to do, would be to send, for example, in our Laplace code, if we want to send a column, we could just use the built-in Fortran 90 array slicing to send as a message type the columns of data. And that is actually not a bad idea at all. It fits perfectly naturally with Fortran and it makes perfect sense in many ways. The only problem is that this actually in Fortran results in a temporary copy being created behind the scenes, and the problem with that is that temporary copy can get deallocated as soon as this routine comes back. Meanwhile, if it's something like an iSend, the data hasn't been sent yet and the temporary copy gets deallocated. So the bottom line of this is that if you're going to use array shaping and slicing in Fortran along with your MPI routines, you want to make sure that the MPI compiler is aware and savvy about it and knows it's supported. MPI has the ability to test that. You can see if MPI subarrays are supported, then things will work properly. Otherwise, you could possibly run into problems using array shaping type of routines. So just be aware of that issue and make sure that you compensate for it or aware that it's a possibility. C++, little bit of bad news here in that the MPI committee, they were big fans of C++, so please do not be irate that support for it was dropped. I mean, C++ performance issues are, it's just part of working with C++, right, is that it's very easy to all of a sudden do something horrendously bad for performance. MPI is no exception. So the committee struggled valiantly for decades to keep the C++ binding working properly. They finally gave up. They deprecated it in 2.2, and as of 3.0, it's now removed. So there's no C++ per se binding to MPI, and it's for all the reasons, again, that C++ programmers are familiar with. You just can't use STL containers as they're meant to be as a pure abstraction and expect that to work with things like MPI or anything else that's really performant. So I'll be glad to discuss any particulars with those of you that are C++ programmers, but basically resign yourself to either using the C API that we've been using in this class so far. That shouldn't be a problem. The Boost one still continues on, which is where, with this. So Boost does provide an implementation which does have a lot of neat things that you would expect from C++ that makes life a lot easier. So here's how you can send a message in Boost. It does a great job of coming up with the default parameters and minimizing the boilerplate code and keeping a lot of the wonderful C++ stuff. So if you're happy just rolling in Boost into your project, great. Otherwise, use the C interface. But believe me, it wasn't for lack of trying to make C++ work properly. There are also lots of other language bindings out there as well. They're not the official ones, but they work just great. People have rolled the interfaces in that work wonderful. These are the ones I'm aware of, some of which are heavily used. So Python and R, I've seen a lot of codes that use MPI. Java, I've heard a lot that use MPI. And there are more out there as well. We're almost out of time, and I'm almost done here. There's a timing routine in MPI that's wonderful. It's a microsecond timer. It gives you a nice portable timer. Everybody uses too few timers in their code. You should have timers throughout your code wherever you think problems might show up. That's a wonderful way to just by default know when your I/O system is behaving badly or whatever. MPI WTime is great to be aware of. It's a wonderful portable timer that's just there. That's always an issue with implementing timers. MPI 3, we've talked about all the new stuff. It's just been seamlessly integrated, so we've covered all of MPI 3. But if you do care for historical purposes, what it brought to the table, it brought in these niftier communication topology stuff, some of the more advanced stuff we talked about. It does not solve the problem of fault tolerance, but at least specifies how things should behave a little bit better. Let's see, anything else? They're smart. The MPI committee has learned over the years to not support things that can't be implemented perfectly and seamlessly. So they unfortunately couldn't do some really nifty stuff involving things like active messages or interrupt-driven messages and whatnot, standard debugger kind of thing. And there's a wonderful debugger we'll look at later today. But they resist the temptation to do things that are wonderful but can't be universally implemented by all the versions in a reasonable amount of time. And the good news is, because of that, is that MPI just everywhere works. Everything we've talked about today, and MPI 3 spec works everywhere seamlessly and portably. It's just not a problem. But again, they skipped a few things that you might hope that they'd rolled in. The Fortran 90 interface, with the Fortran 2008, you can actually roll in some nifty stuff that allows us to skip things like that error parameter that Fortran people are forced to deal with. We could skip that if we care. Array subsections work, as we were just discussing. So Fortran 2008 people that are out there, there's some nifty Fortran 2008 stuff that I won't go into the details of. So which features to use? Of all the routines that are out there, start with the basic stuff that you know about now. Be aware of the others. You can evolve and grow into them as you go along. Be fearless in looking through that index that you've got right now. You should be able to at least understand what almost all of those routines do, the variants that are out there. You click on it, oh, okay, this is the receive, this is the non-blocking receive, or, oh, here's the gather that's, the non-blocking gather versus the regular gather. So you now understand the vast majority of those routines. So I'll leave you with this, and then we can take our break. I'll leave this up on the screen. Here's a good test right now talking about this all reduce that I mentioned yesterday, but we'll mention again today. So remember, it's reduce, except all the PEs get the result of it back. So here's a little fragment of code to test your logic. And we'll talk about this when we come back after the break. So here's your chance to see if you're really kind of getting some of the subtlety. It's not a subtlety. It's, you should understand how this works, but it's not. It might mess with your head a little bit at first. Here's a piece of code. Figure out what the answer is for this all reduce, and I will see you after the break.